Welcome to part 3 of this 3-part series of videos on special relativity. If you haven't seen parts 1 and 2, I'd recommend you do. That way this part will make much more sense. To recap, in parts 1 and 2 I ticked the first 11 boxes in my journey route map as shown here. That leaves only the last and most important box to tackle to complete the journey. I do spend some time after that to help with understanding what special relativity is telling us, which I hope you find useful. Let's now pick the story up at that last box and derive E equals mc squared. Energy is recognizable in a variety of forms, and I've listed a few here. The very fact that it reveals itself in so many different ways does give it a rather ubiquitous nature. In all of the forms shown here, it can be measured in the same units, and it's convertible from one form to another, well, at least in theory. I'm going to consider mechanical energy and use it to push this trolley up a slope like so. The mechanical energy required to do this is simply the force applied multiplied by the distance covered. The units are called joules. Well, they are in the SI system of units anyway. Engineers will also refer to this form of energy as work. Now, we know from Isaac Newton's second law of motion that force equals mass times acceleration, where the units are newtons for force, kilograms for mass, and meters per second squared for acceleration. It therefore follows that 1 newton of force is actually equal to 1 kilogram meter per second squared. 1 joule of energy could therefore be written as 1 kilogram meter squared per second squared. Now, while that works in 3D space, in 4D space-time, time is measured in units of length, namely meters. In this case, joules must be redefined like this. But now we have meters squared on both the top and bottom, so they cancel out, leaving just kilograms. So in 4D space-time, it appears that mass and energy are the same quantity. That gives us a problem, because in 3D space, they are most certainly not the same thing. So I need to find what mass would need to be multiplied by in 3D space for this equation to be true, and based on the units, it would appear to be some speed squared, like this. So now I can make the statement, energy equals mass times some speed squared. Of course, this comes with the proviso that I have to be able to make it work in 4D space-time also. With that in mind, the new question I need to ask is, what speed squared could mass be multiplied by in 4D space-time without affecting the result? The answer, of course, is the speed of light, c. In 4D space-time, the speed of light is just 1, with no units. Hence, c equals c squared equals just 1. By deduction then, in both 3D space and 4D space-time, E equals mc squared. In 4D space-time, it's usual just to write E equals m, because of course c squared is just 1. I should point out that the equation refers to the energy that exists in the form of stationary mass. So it's not to be confused with kinetic energy, or indeed any other form of energy. Oh, and in case you didn't notice, I've done it. I've arrived at the final equation and delivered on my promise. I bet you thought that last step was going to be more complicated than that, didn't you? Oh, and of course, we need to go back to the route map now and tick that final box. Okay, time for a quick confession. The way I did that was a blatant cheat. Messing with the units may have validated the equation, but it's not the way you derive it from first principles, and it's certainly not the way Professor Einstein did it. Einstein first presented the theory of special relativity in a paper in 1905. It was written in German, but in free translation the title was On the Electrodynamics of Moving Bodies. The study was based on an analysis of the forces between electrically charged particles, not mechanical work, and its main aim was to formally unite magnetic and electrostatic forces. E equals mc squared didn't even appear in the text. Rather, it was evident because it showed how mass converts directly into radiated energy. It was only later papers that derived the equation in its more familiar form. Now, I thought it might be interesting, even fun, to make some observations and interpretations that come from the theory of special relativity. I'll do this by asking some questions and then presenting the answers, so here goes. 1. Has special relativity been confirmed experimentally? 2. How much energy is there in 1 kilogram of mass? 3. What would you see from a spacecraft window? 4. Could a spacecraft travel faster than light? And 5. What is a light cone? So, first question. Has special relativity ever been confirmed experimentally? Well, yes. The 3 experiments considered most significantly conclusive were those of Michelson-Morley in 1887, Kennedy-Thorndike in 1932, and Ives-Stilwell in 1938. I'll leave it for you to look those up on Wikipedia if you really want to see the details. Nowadays, special relativity can be seen in action in global positioning systems, sat-navs, nuclear reactors, space exploration, and more besides. What was once the preserve of particle physicists and cosmologists is now just part of the basic curriculum for a whole host of professional disciplines. Question 2. How much energy is there in 1 kilogram of mass? This is an easy one. We just have to put some numbers into the equation. If 1 kilogram of mass could be converted into pure energy, it would yield 9 with 16 zeros after it joules, or 25 billion kilowatt-hours of electricity, or 1,400 Hiroshima atom bombs, and whichever way you look at it, I can safely say it's a lot. The only process I'm aware of that converts 100% of mass into energy is the annihilation of matter and antimatter when the two come into contact. For example, a positron is the antiparticle of an electron, and if the two meet, they annihilate one another and release 2 high-energy photons at the upper end of the X-ray spectrum. X-ray photons, just like light photons, have no mass, and therefore the conversion to pure radiated energy is total. Question 3. What would you see from a spacecraft window? I've been looking forward to this one. What I'm now going to do is show you what you would see from a spacecraft window as it flies past the planet Jupiter at 3/4 light speed. What you see here is the dark side of Jupiter and the Sun just peeping out from behind it. The camera will turn to keep Jupiter in the center of the frame as we fly past. Let's run the video now. The planet's diameter that's parallel to our flight path is shrunk, causing the planet to look like an ellipsoid. Did you see it? Let's rerun that at 1/3 real time and see it again. Watch the shape of Jupiter carefully this time if you missed it the first time. Here goes. Here's some journey data for you. There are 2 frames of reference to consider here, and I'm calling Jupiter the stationary one. Thinking in terms of those rulers we used at the start, the stationary ruler is attached to Jupiter and the moving one to the spacecraft. In that case, the journey length on the spacecraft's instruments was 1.4 million kilometers in 6.2 seconds, and from Jupiter's it was 2.1 million kilometers in 9.3 seconds. In December 2000, that same journey was made in real life by NASA's Cassini-Huygens spacecraft traveling at a mere 11,600 meters per second, and it took 125 days to complete. And finally, just to put things into perspective, a round-trip radio signal from Earth to Jupiter and back would take approximately 80 minutes. I do need to emphasize here that we're only considering special relativity. I've not taken Jupiter's gravity into account, so I didn't include curvature of the flight path, the slingshot effect, or the effects of general relativity. Also, I didn't make any adjustments for the Doppler effect, specifically the red and blue shifts that should have been applied to the color of Jupiter and the Sun. Question 4. Could a spacecraft travel faster than light? No, it absolutely could not. There are two primary reasons. Let's consider reason number 1. Remember the Lorentz transformation? It looked like this. This told us that when we reach the speed of light, time stops and the distance to your destination becomes 0. So you cannot accelerate beyond light speed because you're already at your destination, no matter how far away it is. Reason 2, as if I needed it, becomes evident when I look at Einstein's derivation of E equals mc squared. In particular, the penultimate equation looked like this. There are two things to understand about this. The first is that c squared is not written down because, of course, it's just equal to 1 in 4D spacetime, and secondly, we have a denominator here, square root of 1 minus q squared, where q is my spacecraft's speed. When the spacecraft is stationary, q equals 0, and the equation reduces to just E equals m. However, when it speeds up, then the root of 1 minus q squared becomes smaller and the energy E becomes greater. This means that E is now including kinetic energy due to the speed of the spacecraft. When q approaches 1, light speed, then E will tend towards infinity. In other words, as we approach light speed, the energy required to accelerate that last little bit is infinite, so our spacecraft would simply never be able to do it. Question 5. What is a light cone? Okay, let's start by drawing a three-dimensional frame of reference like this, but where the vertical axis is the time axis, x4, and not the usual x3 space axis. What I've done here is to assume that x3 is 0 everywhere, so we're only allowed to move in the x1, x2 plane. That way I can cheat a little and show the time axis, x4, in a three-dimensional frame, even though we're really representing 4D spacetime. Let's assume meters as our units here, so 1 meter on the x4 axis is the same as 3.33 nanoseconds. Let's make a note of that. Now I'm going to put a point at x1 equals 1, represented by this black dot, and allow it to move 1 meter in any direction. That means it could be anywhere on a circle 1 meter in radius as shown here. But just a minute, I'm looking at 4D spacetime here, so I must know how fast I've moved 1 meter. Let's take the fastest possible speed, light speed of course, in which case I'll have covered the distance in 1 meter, or 3.3 nanoseconds. This means the x4 coordinate is also going to be 1, like this. Let me just record that with this circle here. Now, logically, I'd have covered half that distance in half that time, like this. I'm sure you can see what's happening here. If I keep on building up all the possible cases for places I could reach at light speed, I'd end up generating a conical surface like this. Equally logically, I can look at all the places I've been in the past and show them as the negative half of the cone like this. This is all a light cone is. I've stopped it at 1 meter, but obviously it goes on as far as you want. The only question now is, what's it for? What good does it do us? Well, it's a great way of visualizing the space-time continuum, and in particular, how we must modify our understanding of what time is. No longer can we regard it as a separate quantity unrelated to space. Relativity tells us that it behaves as the fourth dimension of a single continuum, and that requires us to challenge what we previously regarded as common sense. Assume this is your frame of reference and you're represented by the red dot I've just put at the origin. Now, you can remain stationary at the origin of the x1, x2 plane for as long as you choose. However, when it comes to the x4 axis, you don't have such a choice. You advance relentlessly through time, whether you wish to or not. Time and tides wait for no one, as the saying goes. Now, suppose you move 2 meters. Let's suppose you manage that at 5 meters per second, so you'll therefore take 0.4 seconds. I know that 1 meter on the x4 axis is equivalent to 3.3 nanoseconds, or 3.3 times 10 to the power minus 9 seconds. The x4 coordinate would therefore be 0.4 divided by 3.3 times 10 to the power minus 9, which comes to 120 million meters. In other words, your cone would be so slender, with such a tiny cone angle, it would be invisible as a cone. This represents our pre-relativity perception of things, where speeds simply add up and time is not a feature of space. It's only when you speed up to some significant fraction of light speed that your cone would open out and show why speeds do not simply add up. What actually adds up, as we now know, are rotations in space-time planes. Light cones are also useful in general relativity, where it can be shown how gravity distorts space-time, but that's not something we're going to get into here. Well, that's it. I've reached the end. I hope you found this useful, perhaps even enjoyable. As with all of these types of videos, I must ask you to hit the subscribe button if you think it's worth pushing it up the popularity ladder. I promise you I've no intention of making any money out of this. The video is purely a personal objective to create something worthwhile and that keeps me from vegetating in my spare time.